Welcome back to the deep dive. Today we're digging into something pretty fundamental, I think, a paradox with today's AI agents. They can be incredibly smart, clever at following instructions,
Right.
but then faced with something new, a sudden change or an obstacle they haven't seen, they just freeze. They're kind of clueless because their strategy is fixed.
Yeah, that inability to learn right then and there in the moment, that's arguably the biggest hurdle left for truly autonomous AI. I mean, think about us, humans.
Okay.
We try something, maybe we mess up, we think about it for a sec, figure out a better way, and try again, maybe just minutes later. Current agents, they just can't do that rapid internal course correction.
It's not just about raw power then.
No, not really. The core issue isn't always needing more compute. It's about learning efficiently from sometimes just one single attempt, one failure.
So that brings us to our mission for this deep dive. We're looking at this new approach, the Jericho Test Time Learning Benchmark, JTTL, and this framework called EvoTest. It's designed specifically to tackle that rapid adaptation problem.
And importantly, without the usual incredibly expensive process of fine-tuning the entire model every time something goes wrong.
And the really interesting bit, the hook you mentioned earlier.
Yeah. The counterintuitive part is how EvoTest seems to succeed. It's not by chasing those sparse numerical rewards like in traditional AI training.
No.
No, it learns by analyzing the narrative, the whole text log, the story, of its own mistakes. It's learning from failure, but from the description of the failure.
Okay, that's fascinating. Let's start with the test itself, the JTTL benchmark. Why these old school text adventure games, interactive fiction like Detective, Library, even Zork 1. Seems kind of specific.
Well, they're actually perfect for this. These games are complex, the rewards are really few and far between, sometimes you only get points right at the very end.
Right.
So they perfectly isolate this problem of needing to learn on the fly. The setup is key. The agent plays the exact same game, let's say 50 times in a row, K equals 50 episodes.
The exact same game.
Identical initial state every single time it resets. So any improvement you see in score has to come from the agent learning something internally between those attempts. It can't be the game-changing.
Okay, wait. If the rewards are that sparse, like maybe one reward after hours of gameplay, doesn't that just completely break traditional reinforcement learning? How can RL even work there?
Well, that's exactly the point. It struggles badly.
Yeah.
You hit on the core challenge, data efficiency, driven by signal quality.
Ah.
If you try standard online RL fine-tuning, methods like SFT or GRPO, they need a clear gradient signal, a mathematical direction, to update the model's weights.
Makes sense.
But imagine 100 steps in the game, and maybe you get one little +5 reward at step 99. That single, noisy data point. It's just not enough information to meaningfully improve the agent's strategy for the next try. The signal is too weak, too late.
So that really highlights why those standard RL approaches fail here. And I guess even simpler ideas like the reflection methods where the agent just writes a summary of its failure.
Yeah, things like reflection, they help a bit, like modifying the prompt for the next run. But they only tweak one part, usually just the prompt.
They don't change the core logic.
Exactly. The agent might remember it failed, but it can't fundamentally change how it decides things or how much it explores or how it uses its tools or memory. The JDTL setup just ruthlessly shows you need extreme data efficiency. One run, one transcript, you have to squeeze out all the learning you can before the next attempt.
Which brings us neatly to EvoTest, this evolutionary approach. You said it's gradient-free.
Totally gradient-free. It doesn't try to fine-tune the big underlying language model, the LLM backbone. That stays fixed. Instead, it evolves the entire system around the LLM between episodes.
The whole system, how does that work?
It uses this really neat two-agent structure. First, you have the actor agent. Its job is just to play the game using whatever the current system configuration, let's call it chi, is for that episode E.
Okay, the player.
Right. Then, after the episode finishes, the evolver agent kicks in. Think of it as the optimizer, or maybe the coach. It looks at everything that happened, the full game transcript, the narrative trajectory, let's call it TAUI, and the final score, RE. Based on all that, it proposes a revised configuration, GA+1, for the actor to use on the very next attempt.
That separation seems smart, acting versus adapting. But having this evolver, this meta-optimizer, doesn't that introduce new risks? Like, could the evolver overreact to one weird playthrough, base its changes on floozy evidence?
That's a really good question. And the way EvoTest seems to handle that risk is by making the adaptation holistic. It's not just tweaking one knob.
Okay.
The evolver can adjust 4 different aspects of the agent simultaneously. This spreads the risk, you could say. It's not just fixing one potential bug, it's more like editing the whole agent's approach. This holistic agentic configuration tree has 4 parts.
Right, let's break those down because tuning all 4 at once sounds like where the power comes from. First up is the policy prompt. This is like the main instruction sheet for the actor.
Exactly, it's the high-level strategy. So if the actor keeps getting stuck, walking back and forth, or trying useless actions, the evolver literally rewrites parts of that prompt.
Giving it new rules.
Yeah, like adding strategic heuristics, always examine objects before taking them, or, crucially, putting in explicit guardrails based on past failures. Things like, avoid that navigation loop near the library entrance at all costs.
Okay, that's clever. Second component.
Second is the deployment time memory. And this isn't just a raw text log. It's structured, like a little database the agent uses while playing.
What's in it?
2 key parts. A success memory, which logs state action pairs that actually led to a score increase, so it remembers what worked. And a failure memory, which records patterns or situations that consistently led to the agent getting stuck or failing.
So it learns from both success and failure structurally. What's third?
Third, and this is quite meta, is hyperparameters, AG. The evolver can actually tune the LLM's own settings for the next run, like the temperature setting. If the actor was too conservative, maybe stuck in a rut, not exploring enough, the evolver might bump up the temperature for the next episode to encourage more creative or diverse actions.
Wow, okay. Tuning its own brain settings. And the fourth component.
Finally, tool use routines.
Mm-hmm.
This is about refining how the agent uses its own internal tools. For example, how it queries its memory. Should it be a gentle suggestion or a direct command to check the failure memory in a certain situation?
I see.
And this also includes something called the state abstraction logic. Basically, it's a piece of code, often Python, that takes the potentially very long, verbose game history and summarizes it into concise milestones. This helps the actor keep track of the big picture without getting bogged down in details.
So strategy via the prompt, learning via structured memory, exploration via hyperparameters, and efficiency via tool use and abstraction. 4 levers, all pulled by the evolver based on the last run. Okay, so the evolver comes up with maybe a few different potential child configurations based on the last parent run. How does the system decide which new configuration to actually use for the next episode? That sounds like the classic exploration versus exploitation problem. Do you stick with what worked okay or risk trying something new?
Yeah, exactly that dilemma. They needed a smart way to test out promising new ideas, these child configurations, without risking a total performance collapse if the new idea is actually terrible.
Makes sense. You don't want one bad mutation to derail the whole learning process.
Right, so they adopted an algorithm called upper confidence bound, or UCB. It's a well-known approach for managing this kind of trade-off quite elegantly.
UCB, how does that work in practice here? Is it complex?
The core idea is actually pretty intuitive. Think about choosing where to eat dinner. You have your reliable favorite place that's like the parent configuration. You know roughly how good it is, its average score is high. Then there's a brand new restaurant nearby, a child configuration. It might be amazing, but you haven't tried it much, maybe only once or twice.
So you're uncertain about the new place.
Exactly. UCB formalizes that uncertainty. It gives that new, less tested option an explicit exploration bonus. This bonus is bigger if the configuration has been tried fewer times.
Ah, I see. So the score used for picking the next configuration isn't just its average performance so far.
Correct. It's the average performance plus this exploration bonus. And naturally, as you try a configuration more times, that bonus shrinks because you become more confident about its true average performance.
So it encourages trying new things, but gradually favors things that consistently perform well.
Precisely. And crucially, UCB acts like a safety net. It helps prevent those catastrophic drops you mentioned, because the reliable parent configuration, having been tested many times, will likely still have a competitive UCB score, even without a large exploration bonus.
So if a new child configuration turns out to be really bad on its first try,
Its average score plummets, its UCB score drops, and the system naturally tends to fall back to the more reliable parent for the next attempt, without needing anyone to step in and fix it manually. It balances exploring new ideas with the safety of known good ones.
okay, that UCB part sounds critical for stable learning. Now, beyond the elegance and the performance, let's talk practicalities, cost and time. This was RQ3 in the paper, right? How does EvoTest stack up against those traditional RL methods?
Oh, the difference is night and day, and it really highlights why standard RL is often just not feasible for this kind of rapid test time learning.
How bad is it for RL?
Well, those online RL methods,
Mm.
especially the gradient-based ones like GRPO that need backpropagation, they require serious hardware. We're talking 4 high-end NVIDIA H100 GPUs, which are incredibly expensive.
Okay.
And even with that hardware, each learning update, each fine-tuning step between episodes takes about 5 to 10 minutes.
5 to 10 minutes per episode. That adds up incredibly fast if you're doing 50 episodes.
Exactly. That compute cost and time delay is precisely why traditional RL just doesn't scale for situations where you need fast adaptation, maybe in real-world robotics or interactive systems.
And EvoTest. What does its learning step, the evolver's part, cost?
That's the beauty of replacing the complex backpropagation with semantic analysis. The entire learning step for EvoTest the Evolver, analyzing the transcript and generating the new configuration chai, takes roughly 20 to 30 seconds.
Seconds, compared to 5-10 minutes on multiple GPUs.
Yeah, it's essentially the time it takes for a single call to the LLM API that powers the Evolver. So you're swapping out massive, continuous, expensive computation.
For one quick, cheap API call.
Right. It's a fundamental shift from resource-heavy training to very lightweight, language-guided evolution of the agent's configuration. Way more practical.
The performance results seem to back this up too. The numbers were pretty clear, weren't they?
Absolutely decisive. Looking at the area under the curve, or AUC, which measures learning performance over all 50 episodes, EvoTest got the top score on all 6 of the JTDL benchmark games.
All 6. Wow.
Yeah, average AUC was around 0.47 out of a possible 0.50. Compare that to the next best baseline, which is another evolutionary prompt optimization method called EvoPrompt that got about 0.34 to 0.36.
And the online RL method, GRPO?
That lagged even further behind, around 0.30, so a really significant performance gap.
And it wasn't just average performance, right? EvoTest actually won some games the others couldn't.
That's right. It was the only method capable of consistently solving 2 of the hardest games, detective and library. And this really points back to the power of that holistic learning we talked about.
Because it can fix multiple problems at once.
Exactly. Methods that only adapt one thing, like just the prompt or just the memory, they tend to hit a performance ceiling. They fix one bottleneck, but then another one pops up they can't address. EvoTest, because it can simultaneously, say, increase the exploration temperature and add a new strategic rule to the prompt, can overcome these more complex failure modes.
That makes sense. But for me, the most striking insight was that narrative credit assignment. Can you walk us through that library game example again? How did the Evolver figure out something useful without a direct reward signal?
Right, this is super cool. So in the library game, there's this crucial step you have to take. Ask technician about gates. It unlocks progress later, but doing that action gives you 0 immediate points. Nothing.
So a normal RL agent, seeing no reward, would just learn not to do that. It seems useless numerically.
Precisely. An RL agent relying purely on the score signal would likely never reinforce that action. It looks like a waste of a turn.
But the Evolver, using language.
The Evolver reads the transcript. It sees the context. Okay, the agent is near a technician character. The technician seems to be blocking access to the security gates, which seem important. Even without a score change, the Evolver reasons semantically.
It understands the situation from the text.
Yeah, it thinks, okay, interacting with this character, even though it didn't give points now, seems necessary to deal with this obstacle blocking future progress. It discovers the latent value in that action purely by understanding the narrative flow. That's latent value discovery driven by language, not numbers.
That is genuinely impressive. The story itself provided the signal for what was important. And you mentioned it also used this narrative analysis to avoid pitfalls.
Yes, another great example from library. The Evolver noticed a pattern in the transcripts where the agent would try to interact directly with the security gates and get stuck in this endless loop of the game asking for clarification. It wasn't really the agent's fault. It seemed like a quirk or bug in the game's parser.
A system failure, not a strategy failure.
Exactly. So what did the Evolver do? It identified this pattern from the text and then added an explicit rule, a kind of verbal guardrail, directly into the actor's policy prompt. Something like, warning, interacting directly with the security gates causes a parser loop. Do not do this. Ask the technician instead.
So it literally learns to work around bugs or limitations in its environment by writing rules for itself.
Yes. It learns about the environment's quirks and systematically self-corrects to avoid known failure points.
Okay, so let's try and wrap this up. EvoTest really feels like a significant step forward, doesn't it, towards agents that can actually improve themselves on the job.
I think so.
It strongly suggests that this gradient-free whole system evolution, guided by analyzing the rich story of its own experiences, is much more effective and certainly more practical than traditional methods when rewards are sparse and adaptation needs to be fast, like in these test time learning scenarios.
I agree. And it hints at maybe a fundamental shift in how we should be thinking about getting to more general AI. Perhaps the ultimate key isn't just slightly better map for gradients or even just massively bigger models, although those help,
But rather,
but rather endowing the AI with the ability to be its own system optimizer, to use its experience, its narrative, to systematically rewrite its own rules, tune its own parameters, manage its own memory, all in this holistic way. It shifts the focus maybe from just training a static model to enabling ongoing configuration evolution.
that's a powerful idea, and it leaves a really interesting thought for you, the listener. This whole EvoTest process, especially adding those verbal guardrails, it sounds uncannily like how humans learn from big mistakes, right?
Yeah, like messing up financially and then literally writing down a new rule for yourself. Never invest more than X% in speculative stocks.
Exactly.
Yeah.
So the provocative question is, what other complex human learning processes, what other ways we systematically improve ourselves based on experience, maybe planning, summarizing key takeaways, adjusting personal habits could potentially be automated using this kind of whole system, narrative-driven evolution? Something to chew on. Thanks for diving deep with us today.